Okay, lecture 7, linear independence. So in this lecture, we'll basically do definition and some examples. So here's the definition in this nice little box. A set of vectors is linearly independent if the only solution to this equation is k1 equals 0, k2 equals 0, dot, 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 kn equals 0. A set of vectors is not linearly independent. It's called linearly dependent. So what we'll see is that if they're linearly dependent, if a set of vectors is linearly dependent, then one of them, at least one of them, can be written as a linear combination of the other ones. So how do we show that two vectors are linearly independent? Well, the equation is we want to show that this equation has only these solutions. Remember that K1 and K2 are variables here. W1 and W2 are two known vectors, right? We know what W1 and W2 is. So what is this equation? Well, it's K1 times 1, 2 plus K2 times minus 2, 2 equals 0, 0. So that's what this equation is. If I plug in for W1, W2, and 0, those are all vectors. Now, if I multiply this together, what do I get? I get K1 minus 2K2, K1 times 2 plus K2 times 2, so that's my second row. And these are vectors, so I'll put the box around them. So really, we have two equations here that we need to solve for K1 and K2. Okay, so what are the possible solutions? Well, we solve these by setting up augmented matrices and reducing. So our augmented matrix is 1, minus 2, 0, 2, 2, 0. And note that, well, remember that this first column is for K1, the second column is the coefficients on K2, but the coefficients on K1 are just W1. So this column is the vector W1, the next column is the vector W2. So to reduce this, what do I do? I multiply the top one by 2, 2 minus 4, 0, 2, 2, 0, and we'll subtract the bottom row, the top row from the bottom row. 2 minus 4 is 0, and then 2 minus 2 is 0, 2 minus 4 is 6, 0. Great, and I can divide the bottom row by 6 and the top row by 2, so 1 minus 2, 0, 0, 1, 0, and then multiply the bottom row by 2, and then finally add the top row to the bottom row and use that as my new top row. And divide the bottom row by 2. Great. And this becomes a pair of equations. Remember that this is our K1 coefficients, this is our K2 coefficients. So the equations we get are K1 equals 0, K2 equals 0. Only solution is that, which is good. So linearly independent. Are these two linearly independent? How do we show that they're linearly independent? Well, show only solution to K1 V1 plus K2 V2 equals 0 is K1 equals 0, K2 equals 0. Okay, but what does this equation become? Well, that's K1 V1, but V1 is 2 minus 1, 3, plus K2 minus 5 minus 2, 6. We want that equal to 0, 0, 0. And so we can see that this is actually going to turn into 3 equations, K1 times 2 plus K2 times minus 5 equals 0, K1 times minus 1 plus K2 times minus 2 equals 0. That's our middle equation. And then K1 times 3 plus 6 times K2 equals 0. Okay. So we can turn this into an augmented matrix. 2, minus 5, 0, minus 1, minus 2, 0, 3, 6, 0. And then we want to reduce that. Note again that V1 is our first column, V2 is our second column. So what's the easiest way to deal with this? Well, 2 minus 5, 0. I'll multiply the middle row by minus 1 just to tidy up a little bit, and divide the bottom row by 3. And we get that. So easy enough to get rid of the bottom row because we'll just subtract it from the top, from the middle row. And we get 2 minus 5, 0, 1, 2, 0, 0, 0, 0. It's important that we have zeros here on the right-hand side, because if we got some kind of weird number here in the bottom right, then there'd be no solution. So how can we finish this off? We will multiply the second row by 2. And we will subtract the top row from the second row to get 2 minus 5, 0. And then the new second row will be 2 minus 2 is 0, 4 minus minus 5 is 9, 0, 0, 0, 0. And then finally, you can rewrite this as 2 minus 5, 0, 0, 1, 0, if we divide the middle row by 9. And then subtract 5 times the middle, add 5 times the middle row to the top row. That gives me 2, 0, 0, 0, 1, 0, 0, 0, 0. And then finally divide the top row by 2. And there is my reduced matrix. And what is the solution? K1 equals 0, K2 equals 0. So these are linearly independent vectors. Show that these are linearly dependent. Well, we've seen enough of this now that we know what the process is. No, these are W's. W1, W2 plus K3, W3 equals 0 has more than one solution. We know that 0, K1 equals 0, K2 equals 0, K3 equals 0 is a solution, because 0 times 0 times anything is 0. So are there more than one solution, right? If there's only that one solution, then they're linearly independent. So we set up a matrix, augmented matrix like this, and we say, okay, well, we need to reduce this. But I know how reducing this goes, because we've done a bunch of these. I'm going to get this, right? And this column, these will be numbers of some sort, right? That's what the asterisks represent. But the column won't have any of these leading ones in it, right? This leading one and this leading one tell me that K1 and K2, we're going to depend on K3. So we have a parameter. So there'll be infinitely many solutions. So our vectors are not linearly independent. They're linearly dependent. So how to tell if a set of vectors is linearly independent? You follow these steps. You create a matrix whose columns are the vectors and reduce the matrix. If you get a parameter, they are dependent. So this set of vectors, is it linearly dependent? Well, we set up the matrix whose column is the 3 vectors. And we think about what happens when we reduce a matrix that's got more columns than rows. Well, the best you could hope for would be something like this for the first 3 columns. And then the last column would have to be some numbers. And that tells me that there'll be a parameter. And so we are not linearly independent. Right? If you tried to solve that for K1, K2, K3, K4, you'd actually get infinitely many solutions. So the dimension of a vector is the number of components it has, assuming that it already has finitely many components. Assuming that it has finitely many components. So if you have more vectors than the dimension of the vectors, right, then that means we have a linearly dependent set. So dimension of vectors equals number of rows number of vectors equals number of columns. Right? Because we want a column for V1, a column for V2, dot, 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 a column up to Vn, and then our zeros here. So if I have n vectors, there's more vectors than dimension. If I have m entries in each vector where n is bigger than m, right? So I've got more vectors than the dimension, then what does that mean? Well, when I reduce it, I'm going to end up with some parameters here. And that always happens. And so, right, they can't be linearly independent. They have to be linearly dependent. If you have fewer vectors than dimension, what we can say about linear independence? Not a whole lot. If I have, say, 2 vectors in 3 dimensions, right, I could have numbers, say, V1, V2, V3, that's 1 vector, W1, W2, W3. If I think about what the reduction of this can be, one reduction of it is 1, 0, 0, 1, 0, 0. But another possible reduction would be 1, 0, 0, and then a number here, and zeros down here. And that tells me that there's a parameter. So they're not linearly dependent. And the second case happens if we take, say, a vector v equal to 1, 1, 1, and a vector w equal to 2, 2, 2. Are these linearly independent? Is the only solution to K1v plus K2w equal to 0 is the only solution to this K1 equals 0, K2 equals 0. And no, you can see pretty clearly that W is just a multiple of V. If we take K1 equal to 2, K2 equal to -1, is also a solution. So these are linearly dependent. So if I have fewer vectors than dimensions, they might be dependent, they might be independent. If I have more vectors than dimension, then there definitely are dependent.